Hey everyone, welcome to Mad Bars, where we decode the mysteries of time complexity with a dash of humor. Today, we will embark on a thrilling journey through different code snippets to understand how time complexity works. Are you ready for some coding fun? Let's dive in. Alright, let's start with the classic one. Here's our first code snippet. We have a function called foo that takes an array and its length as inputs. It calculates the sum and product of the array elements using two separate loops. Now, can you guess the time complexity of this code? Let's break it down together. The first loop iterates length time to calculate the sum, and the second loop also iterates length time to compute the product. As a result, both loops have a time complexity of big O n, where n is the length of the array. Now, you might wonder why we use big O n to represent the time complexity. Well, welcome to the magical world of asymptotic notation. The big O in big O n stands for the order of. It tells us the upper bound or worst case behavior of our algorithm. In our case, as the input size array length n increases, the time taken by the algorithm grows linearly with n. Alright, buckle up for the next challenge. Here we have a function called func that takes an integer n as input. It uses nested loops to print pairs of numbers. Now, what's the time complexity of this snippet? Let's break it down. The outer loop runs n times, and for each iteration, the inner loop also runs n times. So the total number of iterations is n multiplied by n, which gives us big O n raised to power 2 time complexity. In asymptotic notation, we use big O n raised to power 2 to represent the worst case behavior of our algorithm as n grows. It's like watching a dazzling fireworks show of loops. Behold, function a recursive marvel. It's like a labyrinth of function calls and it generates random numbers along the way. What's the time complexity of this recursive adventure? Let's find out. This code, the function generates random numbers and calls itself with modified parameters. The time complexity of this recursive function is hard to determine precisely, but it's approximately big O 2 raised to power n, where n is the input value. Using big O 2 raised to power n in asymptotic notation tells us the time taken by the algorithm grows exponentially with n. It's like exploring the ever expanding universe of function calls. Last but not least, let's explore the world of trees. This beautiful snippet represents a binary tree sum calculation using recursion. What's the time complexity of this tree-tastic adventure? Let's unveil the magic. In this snippet, the sum function traverses the binary tree using recursion. The time complexity depends on the number of nodes in the tree. Assuming a balanced binary tree, the time complexity is big O n, where n is the number of nodes. Using big O n in asymptotic notation represents the linear growth of algorithm with the number of nodes in the tree. It's like delving into the beautiful branches of time complexity. And there you have it, folks. We have journeyed through various code snippets and decoded their time complexities. We hope you had as much fun watching as we had creating it. Remember, asymptotic notations help us analyze the efficiency of algorithms and understand how they perform with large inputs. So keep exploring the wonderful world of programming and optimization. Don't forget to like, subscribe, and share this video with your friends. Until next time, this is Matt Bytes signing off. Happy coding!